hybridization, so let's think about this structure. So when sp2 hybridization, those three hybrid orbitals are in a plane. They make it trigonal plane because trigonal planar electron domain geometry. So these three are in a plane. So if I try this, let's see, I'm going to have, so I have a carbon here, and that carbon is going to have an sp2, and then I'm trying to make a nice triangle for you, like that. Not bad, all right? And that has, there's 3 electrons in there. So there's an electron there, an electron there, and an electron there. That's one of the carbons. The other carbon is identical. So the other carbon over here, not quite as good. Sorry, okay. Paired. Is everybody okay with that? Yes? Yes? All right. Now, hydrogen in here is a 1s, so we just use that. There's no hybridization on hydrogen, so we just use the 1s orbital for hydrogen. So each of these is a hydrogen, just labeling them. We've got our carbons labeled. Okay? And that right there is the sigma bonding network in ethylene. I can draw this again. I've got carbon, carbon, and I've got, and this is all in a plane the way I have it drawn, right? And so then I have a single bond to hydrogen, a single bond to hydrogen. Now what I'm going to do is draw this. It's flat. I'm just going to rotate it 90 degrees for a reason. So instead of these hydrogens being flat in the plane, I'm going to rotate so they stick. Actually, I'm sorry, they're up and down, and I'm going to rotate them like this. So one hydrogen sticks out at you, and the other hydrogen sticks back at the board. I'm trying to show the geometry a little better. Everybody okay? Same thing. This is flat, this is flat, this has just been rotated. Now, we're not done. There's electrons left over. Each carbon has a p orbital with an electron in it. Both carbons have this. And if the 3 sp2 hybrid orbitals are in a plane, a trigonal plane, where's the p orbital? If here's 2 and behind me is the third sp2 hybrid orbital, what represents the p orbital? Me, my body. The p orbital is orthogonal to the plane that the hybrid orbitals are in. Go back and look at when we did an sp2 hybridization for the first time. That's what we drew. We drew the 3 sp2 hybrid orbitals in a plane, and the p orbital is sticking out of it. So what that means is that the p orbital here is up and down in the plane of the paper. Everybody okay with that? This guy's flat, this is sticking out and back. The p orbitals are in the plane. And what you have is an electron here, and this is an overlap, and this is an overlap. I didn't get them close enough to draw the lobe overlap like I should. Sometimes we indicate this with a line. We indicate that overlaps and that overlaps. All right? And so now I took care of these 3 and this. So what I now have is this carbon-carbon interaction. There's the sigma part of the pi bond, and this double lobe overlap is the pi bond. The sigma is a pair of electrons, the pi is a pair of electrons. There's your double bond. Everybody okay on that? We use the electron domain geometry to predict the hybridization, which led to extra p orbitals with electrons in them that then we could use to make a pi bond. Let's make a triple bond. Let's do acetylene. So if you look at acetylene, acetylene torches, right? Acetylene is also a gas, C2H2. It's a carbon-carbon triple bond. Ultimately, you get there. All right, so what is the hybridization on carbon? Anybody? sp hybridization. 2 domains, a bond and a bond, right? 2 domains, a carbon over here and a hydrogen there. So I need two domains, 2 atomic orbitals to make 2 hybrid orbitals. So I'm going to grab these 2 atomic orbitals. You always start with the s, and as many p's as you need.
These combined to give me, I used an S and a P, so they're sp hybrid orbitals, and I just left those extra two p orbitals left over. I have 4 electrons, 1, 2, 3, 4. Carbon doesn't have a lone pair, spread them out. Any question on this so far?